Okay, in lesson 7, we talked about how we could use information from a single sample to draw a conclusion about a hypothesized mean of a population. Oftentimes, though, we're faced with trying to compare two different populations at the same time. So in this lesson, we're going to discuss how do we compare two different sample means, or means from two different populations. For example, maybe I have a variety of wheat and I'm looking at the yield potential for a couple different varieties. And I want to know if the new hybrid variety I've produced or created will provide a higher yield than the current widely used uh, variety of wheat. Well, how do I measure that? It's not just enough to look at historical information that says, okay, this is historically what the current version has yielded. I need to put things on the same basis. So I need to plant them in similar conditions in the same crop year and then compare the average yields that I get. That would be an example where we were comparing two means. We're going to have two different scenarios that we need to look at. One in which the two populations or the samples from the two populations can be matched up with each other, or when they're independent of each other. The easier case is when we have dependent samples, or something called matched pairs. To tell if it's a matched pair, you will see something in the wording of the problem that says, we did an experiment and we collected data as pairs of data. So you'll actually see the word pairs, or something that says matched. Another indication would be with or without. So we have, or before and after. So an example of this would be studying the effects of a weight loss treatment. And we would take their measurement of weight before they started the diet and after they started the diet. For each individual, we have two readings, so there's a way of matching those up. Or if we're wanting to know if an additive to our fuel will help us increase our gas mileage, we may look at what our gas mileage is before using the fuel additive and the gas mileage we get after that. Again, there's a way of matching that data up. So when we have a way of pairing the information together, that's called dependent samples. Right? Knowing the weight after the diet plan is going to get matched with the weight before. In order to have the after, I have to have some corresponding value to match it up to. So the after weight will be dependent upon the before weight. The nice thing about you doing a hypothesis test for a matched pair is that we really end up reducing this down to the one sample case that we've dealt with before. And when we talk about a test of hypothesis for two sample means that are dependent upon each other, what we're really saying is we're trying to use statistical inference on matched pairs of data to come up with a conclusion. We will end up using the same procedure as we did on a single population. We'll create a new population by looking at the differences of the before and after, or the two values in the pair. So the method we're going to use for testing the hypothesis regarding the difference of two means using a matched pairs design is we're going to take the two samples, We're going to line them up as the pairs that they are. We do need to collect the information using a random sample process. The data do need to be matched into pairs. We're going to assume that the differences are normally distributed with no outliers or the sample size is large, and that the sample values are independent of each other. What we mean by that is that when I look at, take my weight example again, that the two different people in the study where I have a before and after for each of those two individuals are independent of each other. So we want data to be matched in pairs. We want the data to come from a random sampling process, and we want the differences to be somewhat normally distributed. Just as before, we're going to have three different cases. Either a not equal, which is two-tailed, a less than, or a greater than. The difference here is because we're looking at the difference between the two, the null hypothesis will always be the same for any matched pair example. We'll be using the null hypothesis that the mean difference is equal to 0. Why does that seem appropriate? Well, what we're really trying to do is see if there's a difference in the means of the two populations. If we make the null hypothesis, which is the status quo, that there is no difference between the two populations, then the mean difference would be 0. So the mean difference equaling 0 is equivalent to saying that the two populations have exactly the same mean. Just as before, we need to select a level of significance, alpha. We're now going to calculate a test statistic, and we're going to do that by looking at d bar over s sub d over the square root of n. Now that seems like we have made some changes, but really we have exactly the same situation. We have that t, hold on, we have that t is equal to the observed sample mean of differences, d bar, minus our hypothesized mean of 0 over s sub d divided by the square root of n. Again, that's exactly the same statistic we had before. The only difference is that instead of using x as our variable, we're using the variable d to represent the difference. Instead of talking about the standard deviation of the sampling distribution for the mean, we're now talking about the standard deviation for the sampling distribution of these average differences. So it's still the exact same test that we did before. It still follows a t-distribution. It still has n-1 degrees of freedom. And the values d bar and s sub d are the mean and standard deviation of the difference data. We can then go back to exactly the same process that we did before. We can use the t-table with n-1 degrees of freedom to find a critical value. For a two-sided test, we'll have two critical values because we can either go too far to the right or too far to the left. And notice there, to get the column that we look in our t-table, we have to take the overall level of significance and divide it by 2 because we could go either left or right. For a one-tailed approach, all of the area is going to be pushed down into one tail. So we will use the alpha column for the number of degrees of freedom that we need. That will give us a t-value. If we're looking at a left-tailed test, we'll need to talk about that being a negative t-value because we'll move out to the left. You can remember t tells me the number of steps I can go away before I think there's a problem. The sign just tells me if I'm moving left or right. A minus says I'm going to move out to the left. For a right-tailed test, I will have t being greater than t alpha. So if I get further out than this value, I know I'm going to reject my null hypothesis because that's going to be more rare. And again, I can just look that up in the alpha column of whatever degrees of freedom row I have in my table. So kind of stating that in more general terms, if my test statistic is either too far to the left or too far to the right, in a two-tailed test, I'll reject the null hypothesis. In a left-tailed test, if my test statistic is too far to the left, I'll reject the null hypothesis. And if in the right-tailed test, my test statistic, t sub 0, is further out to the right than I allow, then I'm going to reject the null hypothesis. So all of that is the exact same as one sample that we did before. The only difference is in how we calculated our test statistic, where we've now used the sample differences and come up with the average difference and the standard deviation of the difference in order to plug that into our test statistic. So we're now using the average value of difference and the standard deviation of those differences in place of x bar and s that we had previously. Again, remember that we hypothesized that the mean was 0, so this is really just t bar minus 0. For the p-value approach, it again follows the exact same process. We have our test statistic. We go to this row of our t-table. We try to find the value of our test statistic here, and we sandwich that value, and we then look at the top of the columns to figure out what our p-value might be. If it's a one-sided test, we'll just take those values and that'll be the interval. If it's a two-sided test, we know that will give us just half of the p-value, and so we'll need to double it. So again, we'll look up this value in the table. For a two-sided test, we'll then double the p-value to get it the overall p-value. For a one-sided test, we'll look up the value in the table, and that will give us the p-value. We'll also, when we do lab, talk about how we can use technology to help us come up with the p-value exactly rather than by using an interval. Just as before, if the p-value is less than alpha, we'll reject the null hypothesis. If it's not less than alpha, or if it's greater than alpha, we will fail to reject the null hypothesis. So once we do that comparison, we'll state the conclusion. So again, we still have the same process that we can go through. One, calculate a test statistic using now the differenced data, so the average difference and the standard deviation of the difference. We can then either choose to take the classical approach, where we will compare that test statistic to some critical value and make a decision, or we can use the p-value approach, where we take the test statistic, find the probability of observing that value, given that the null hypothesis is true, and then make our decision on whether or not to reject the null hypothesis based off of the frequency with which we would have observed the samples that we had. So this is, again, a robust procedure. If we do have outliers, we should not be using this procedure. So here's an example. We have some data that shows the cost of a one-night stay in Hampton Inn hotels and La Quinta Inn hotels for a random sample of 10 cities. We're going to test the claim that they are priced differently, so that Hampton Inn is priced differently than La Quinta at an alpha equals 0.05 level of significance. Notice that this is a two-sided test because we just said priced differently. We did not say that we thought one was going to be higher than the other. So there's no indication of direction. So priced differently just means I have a two-sided test. So we're going to select some cities at random that have both a Hampton Inn and a La Quinta Inn. We're then going to collect the price of each hotel in each of those locations. So notice there is a way of matching the data points. These two came from the city of Dallas. These two came from the city of Tampa Bay. So the values that we had depended upon the city within which we took our measurement. There were matched observations, so these are dependent samples. If we calculate the difference, you'll notice that between here, the first one, Hampton, is $24 higher. Tampa Bay, the difference is $53. In St. Louis, the difference is $100. In Seattle, the difference is $40. In San Diego, the difference is -10, and so on. So we end up with this as our list of differences. So if you were to take Hampton minus La Quinta in the previous slide, you would get those values. And how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 data points. Taking the average of those differences gives me 51.4. The standard deviation of those values is 30.8336. We can check to see how well the model fits the normal assumption by looking at what's called a normal plot. And this looks reasonable. Everything's in my little band here. And again, we may, if we have time, talk about that in a lab. But going back to the mechanics of the test, remember our null hypothesis is that there's no difference between the two prices of hotels. The alternative is that there is a difference between the prices. We have a level of significance of 0.05. Our test statistic uses d bar over s sub d over the square root of n, giving me this 51.4 over 30.8336 over the square root of 10, giving me a test statistic value of 5.27. So that means that the difference is 5.27 steps away from the mean of 0, a hypothesized mean of 0. If we go to our t-table, we had 10 observations, which means we have 9 degrees of freedom. We know that we had a two-sided test, so our 5% level of significance is split between the two ends. So we know we're going to have a 0.025 column that we're going to need to look at. So we're going to go to the 9 row and the 0.025 column, and we see a critical value of 2.262. So that says that we could go up to 2.262 steps to the right or to the left before we would consider there an issue, before we would have enough evidence to say that the null hypothesis is false. Because our test statistic is further out, we're more steps away from the mean of 0 than what we're allowed, we will conclude that the null hypothesis is false, and we have evidence to say that the mean difference is not 0. In other words, the average price for Hampton is not the same thing as the average price for La Quinta. So again, since 5.27 is more steps away than the 2.262 we're allowed, we'll reject the null hypothesis. For the p-value approach, we would again go to this value of 5.27 we have, and we would look at our table along the 9 row, and we can see that 5.2 is further out, it's bigger than this 4.781. So I know that the p-value has to be less than this 0.005. So I know p is less than 0.0005. And again, that's the area in one tail. So to get the area in both tails, we know that the probability from our table, we know that one tail, that p is less than 0.0005. So overall, in two tails, p is less than 0.001, which is twice that value. Having the table, that's the best that we can do. We would still be able to come up with the same conclusion. A probability of 0.0001 is extremely small. That's 1/10 of 1%. So less than 1/10 of 1% would we have observed the samples that we did and the averages hotel price actually be equal. Because it's not very likely we would observe that. This p-value is very small. We will reject the null hypothesis in favor of the alternative. If you have a calculator or other technology, I can do better than this less than 0.005. I can get that it's actually 0.00026, so that the p-value then is 0.00052. For our purposes with the table, this is as close as we can get. If we're using technology, we can get a more accurate answer. But again, since the p-value is less than 0.05, we're going to reject the null hypothesis. And given the fact that it's so small, we would strongly reject that null hypothesis. Again, the p-value gives me a strength of my argument. So we do have that there is sufficient evidence to conclude that Hampton Inn hotels and La Quinta hotels are priced differently. You could go back, if you would like, and think about the fact that, okay, I think Hampton might be a higher quality hotel than La Quinta, and so I have a feeling that the Hampton price on average will be higher than the La Quinta price. Or that, in other words, the difference, Hampton minus La Quinta, would be a positive value. If I change the null hypothesis here to greater than 0, it now becomes a one-sided test. It's still the same test statistic. The only difference is now, instead of getting a t-value of 0.025, we would get a t-value of 0.05, and it would only be one-sided. A t-value of 0.05 for 9 degrees of freedom would be 1.833. And so we could come down here, and it's not going to let me change that. My critical region then would only be the region to the right here, and this would be 1.833 instead of 2.262. What I'm trying to point out is the process that we go through works the same regardless of the type of test that we have. The difference comes in, how do I distribute my critical region? Is it going out either way, or is it just on one side to the right or one side to the left? That will dictate what critical value I use. Well, that concludes our discussion of dependent samples and hypothesis testing for two population means using dependent samples.